Well, good morning, Prealgebra students. This is now lesson 10. Note this is the last lesson we're going to cover before the test. Awesome. Okay, so our objective for today is what are rational numbers and what are equivalent fractions. So first of all, let's start off right here with rational numbers. Rational numbers are numbers that can be expressed as a ratio of two integers. Notice the word rational kind of has that word ratio in the beginning of it. So just think about numbers that can be expressed as a ratio. Remember, a ratio is two numbers compared by division. So 1/2, that's a ratio. It means it's a rational number. 7/16, 31/32, 43/1, which is actually just the same thing as 43. And 4/2, which is actually the same thing as 2. All of those are rational numbers, which brings us over here to our little box thing that I created that looks super awesome. First of all, here's the smallest set of numbers that we defined. And these are just natural numbers. These are numbers like 1, 2, 3. The things we naturally count with. Like chairs. You can count 1, 2, 3, 4, 5, 6, 7. There's 10 chairs. Excellent. But we realized at some point, hey look, we also need to be able to say there's no chairs in the room. So this is what we call whole numbers. That's the next setup. These are ones with 0, 1, 2, 3, 4. So it's actually just natural numbers with 0 added. So notice all the natural numbers are also in this whole number category. So if you name a natural number, you're also naming a whole number. Okay. Then we also started realizing that if we're borrowing from people, or if something like that, you're going down or backwards or something, then we might need negative numbers as well. And that's where integers come in. Integers come in. And that's where we have, notice all these numbers, 0, 1, 2, 3, 4, are out here. But then we also have the negatives of those. -1, -2, -3, etc. So this is what we call integers. And then, a bigger category, we realized, well, what if we cut a chair in half? Then how many chairs would we have? Well, we would have half a chair. Well, that's not in here, so then we have to start including things like that in this category here of rational numbers. So we have things like 1/2, 3/4, 7/8, etc. But notice, we still have things like 4 and things like 0 or 32 that are also in that area of rational numbers. So anything I name in any of these smaller boxes is also going to be in that bigger box. Excellent. So, for example 1, we're just trying to name all of the names that we can apply to these numbers. So first of all, let's look here at A. It says -14. Again, this is like example 1. -14. Well, is it going to be in here? No, because it's negative. Is it going to be in here? Again, no, because it's negative. Is it going to be in here? Well, yes. I have negative numbers. Leave that. It means negative number is going to be over there. So I'm going to include integers in there. It's an integer. Well, is it also a rational number? Well, yes, because notice if I did this, -14 over 1, that's still the same thing as -14. So it would also be a rational. Awesome. Now let's look at B. Alright, B, 6. Well, is it going to be in this first category, a natural? Well, yes it is, because if I just start counting things, 6 is going to be one of those options. So I'm going to say natural. Well, and if it's in the smallest one, isn't it going to be in all of the other ones? Yes, of course it is. Alright, moving on then to part C. C, well, is it going to be in here? In the natural numbers? No, because it's a fraction. And that doesn't reduce down, which we're going to talk about here in a second. So it's not there, it's not whole numbers, it's not integers, it's just a rational number. Excellent. Moving on. Alright, now, I just used the word reduce or simplify down. So think about I've drawn these 3 beautifully colored circles, done perfectly. This first one is colored half full, because I have one of them colored of the 2 pieces that are there, 1/2. This next one, there's 4 equal pieces, exactly, and there's 2 of the 4 colored. And then this one has 6 equal pieces, and 3 of the 6 are colored. But as you look at these 3 pictures, we notice that all 3 of them are the same. So we could say that all 3 of these are equal. So if they're all 3 equal, which one am I going to use? Well, the easy answer is going to be, well, obviously the simplest one. Well, which one's simpler? It's all just a number divided by a number. So which am I going to pick? Well, I'm going to pick the simplest one. So how do we define the simplest one? I've kind of wrote that out here. We're going to go with prime factorization. Oh, that's from the last lesson. Okay. So think about this. What is prime factorization of 1? Well, just 1. Prime factorization of 2? Well, just 2. What about 2? Well, it's 2. 4 is 2 times 2. Well, if I write this, then notice I can go to this. Notice this 2 and this 2 is right here. This 2 and this 2. Let me circle those. Those are right here. So where'd that 1 come from? Well, 1 times 2 is the same thing as 2. So I just wrote it there to make the fraction look normal. And then we notice here that that second one that I circled right here is actually just 2 divided by 2. 2 divided by 2 is simply 1. So 1/2 times 1 actually just gives us 1/2. Same thing down here with the 3/6. We get that 3 over 2 times 3, because 6 is 2 times 3, which is 1 over 2 times 3 over 3. Well, 3 over 3 is just 1, so it's going to be 1/2 times 1. So it's just going to give me 1/2. So which one would I use? I'd use the simplest one, which is just simply 1/2, because those all, we use the word reduce. We reduce. Reduce, reduce, reduce. Some people use the word reduce as kind of like a magic trick. Hey, look at this magic trick. I can reduce these and eliminate things. Well, yes, but because the top and the bottom divide out to 1, and 1 times anything is just itself. So please use the word reduce. Don't use the word cancel. That's a bad word. Sorry about that. Okay, moving on to example 2. It just says simplify this fraction by using its prime factorization. Well, here we go. It gives us this nice fraction here of 72 over 108. So we're going to go back to our factor trees, which we learned about earlier, and we're just going to find its prime factorization. So as I go down, I'm just going to, I've already done them to save some time, I'm just going to circle all of them that are prime and write them in order. 2 times 2 times 2, and 3 times 3. Write them all out there. Same thing with the 108. I have 2 times 2 times 3 times 2 times 3. 2 times 2 times 3 times 2 times 3. Alright, so now we're going to think about our ones dividing by itself, kind of like we did over here. 3 over 3 is 1, 2 over 2 is 1. So we're going to do the same thing right here. 2 divided by 2, well, that's just a big 1. 2 divided by 2 is just 1. 3 over 3, that's just 1. And 3 over 3, that's just 1. So what's left? Well, a 2 and 3. So there I've reduced that down. This big fraction, 72 over 108, is actually just the same thing as 2/3. Alright, so a couple other terms you need to learn are improper fractions. Actually, I'm getting ahead of myself. We need to compare fractions. And one of the easiest ways to compare fractions is to get the same denominator, because remember the denominator tells us about how big each piece is. So if I can compare them to the same size of pieces, then it's easy to see which one is bigger or smaller. So one of the easiest way to do that is just to multiply by the other one's denominator. What'd I just say? Here's 2/3, here's 3/4. So I'm going to multiply this one, the 3, by 4. That one's denominator. Multiply this 4 by 3. That one's denominator. But I can't just multiply the bottom by 4 and not do something with the top. So what I'm going to do is I'm actually going to multiply it by 1. Well, I said 1, but I wrote 4 over 4 and 3 over 3. Well, actually, 4 over 4 is actually the same thing as 1. Right? So as I multiply 2/3 by 4 over 4, it's just going to be the same thing as 2/3. I'm still the same number because I'm multiplying it by 1. It's just going to look different. Same thing over here, 3/4 times 3 over 3, which is 1. It's going to still be that same number because I'm multiplying it by 1, but it's just going to look different. I'm changing its clothes. You're still the same person if you change clothes. So notice I just multiply this by 2 times 4 is 8, 3 times 4 is 12, 3 times 3 is 9, 3 times 4 is 12. So now this fraction is the same as this one, and this fraction is the same as this one, but notice the denominators are the same. So this is saying if I have 9 pieces of a 12-piece pie, and this says I have 8 pieces of a 12-piece pie, which one is bigger? Well, obviously the one with 9 of the 12 is going to be bigger than the one with 8 of the 12. So that one's going to be the bigger one. Okay, moving on to what I was trying to talk about earlier. Improper fractions. Improper fractions are when the numerator, or the top, is bigger than the denominator, or the bottom. So if the bigger number is top, the bigger number is on top, then we call that an improper fraction. Mixed number is a whole number plus a fraction. And I have some examples here. So improper fraction, 12 over 3, 15 over 2. A mixed number would be 2 and 1/2, 7, 13, 16, etc. Okay, so that brings us to example 5. Example 5 says, express the improper fraction as a whole number or a mixed number. So I've went through a lot of the work, so that way you already know how to do this, because we're just doing division. So here we go. I said 11 divided by 5. Well, 5 goes into that 2 times. 2 times 5 is 10, and I get a remainder of 1. So where before we used to stop at that point, we're now going to write this as a mixed number. So notice my remainder of 1, which is down here or right here, is coming right here to the top of my fraction, because that's how many pieces I have left over. My denominator right here is coming from here, what my denominator was originally. Okay, so my denominator stays the same. And then my big number is how many times it goes into there completely. So that's 2 and 1/5 goes in there 2 times, and then there's 1 of the 5 still left over. Hope that makes sense. Look in your book, they explain that a little bit different way with pictures of circles and things. I just don't want to draw that out. This is how I learned it. But if you want a different way, look through your book at example 5. Same idea here for part B. I just did 20 divided by 4. Well, 4 goes into 20 5 times. 5 times 4 is 20. Whenever I subtract those, I get a remainder of 0. Now, obviously, we don't ever write 5 remainder 0. 5R 0. So then what we end up doing is, why would we write it like this? So, but still same scenario, that 5 comes from how many times it goes in here. That's right here. The remainder, which is 0, comes right here. And then my denominator stays the same. Okay? But of course, we wouldn't just, since we wouldn't write that remainder up here, we wouldn't write it 0/4. Why would we need to even say that? We'd say that it is 5. So this one on the left came out to be what we call a mixed number. This one over here came out to just be an integer or a whole number. Good luck. Boom, your homework is on page 66. You do all the 10s, you do all the 9s, and then 9 more. I know you're going to do awesome. Good luck, guys.